Students, good evening. Keep your videos on. Students, till where we have discussed, after a long time we are meeting, right? So till where we have discussed, we are in metallurgy chapter, correct? Yes. Tell me, students, till where we have stopped, where we have discussed.
Smelting.
Yes, Anika, are you talking?
Smelting.
No, I can't hear.
Melting, ma'am.
Can you hear me?
Yes, ma'am.
Any other students? Yeah. Shivatsa, can you speak something?
Some symbol, ma'am. I can't see anything else.
1 minute. I can't hear. 1 minute. I'll check. One minute, students. Yes, students, can you speak once?
We were in smelting.
Yeah. Okay. Okay. Yeah, I can hear. Students, all students, keep your videos on. Students, just glance all this process, metallurgical process. So we are in metallurgy chapter. Okay. So metallurgy means extraction of metal. Students, the first process is nothing but mining. Okay. Mining process. Okay. So after this mining, you will get some chemical substance. Okay. You will get chemical substance. The 1 minute. Yes, Anika, can you make me host?
Yes, ma'am.
Yeah. Yes, thank you. Yes, students, first go for mining. You will get some chemical substance. The name of this chemical substance is nothing but mineral. Okay. All you can't extract. Yes, you can extract, but you need to apply more energy or else more money in the extraction. So therefore, if you want to select or else if you want to extract metal, so you have to select a proper ore. Okay. So all minerals are not ore. Students, you select a proper ore. So then the impurity which are present in this, okay, the impurity which is present in this is called gangue. Okay. So the impurity present in this is called gangue. Then students, ore is the one where you can extract metal conveniently as well as economically, correct? So extraction of metal from ore, so this process is nothing but metallurgy. Okay, so this process is nothing but metallurgy. In case of metallurgy, see there are two types of metals, so free metals as well as combined state. Okay, so no need to apply this metallurgy concept for or else a process for free metals. Okay, if it is there in the combined state, okay, combined state, so you can apply this method. So in this there are four main process are there. So the first main process is nothing but what you have to do, students. After mining, select a proper ore and then crush it to prepare a powder. Okay, so the first process is nothing but a powder. Okay, so you have to prepare a powder of ore. Powder of ore. This is the first major process in case of metallurgy. So the second major process is nothing but you have to remove the impurity, correct? So that process is called concentration of ore. What do you mean by concentration of ore? Concentration of ore in the sense it is a removal of impurity, okay, or else a gang particle. So maximum amount of impurities are removed in this situation. Students, we have studied 5 different techniques. One is simple hand picking method. 1 minute. One is simple hand picking method and one more is a now. Can you see the slide now? Is this clear
Yes, ma'am.
now? You can't see? 1 minute, students. Now we can you see now? You just check now. You speak, students.
Yes, ma'am. Now we can see.
Okay. So now you feel like a box is covered. Some box is covered. Okay.
Yes, ma'am.
Yeah. Now is it clear?
No, ma'am.
No, ma'am.
Yeah. Now it's clear.
Yeah. So box in the sense it's actually your picture. I'm concentrating on your faces. So that will come in the form of a box. Okay. Yes, I have to see you, right? Yes.
Again, we can't see, ma'am.
Is it now?
Yeah, ma'am. It's proper.
Yeah. So students, now the second process is nothing but concentration of ore. So that is nothing but a removal of impurity. So we have studied different techniques. So 5 different techniques we have studied. So one is nothing but simple hand picking. Okay. The second process is nothing but levitation process or else gravity separation, hydraulic washing. And third one is magnetic separation. Fourth one is froth flotation process. And the next one is a leaching process. We have studied all these things and it has its own. Yeah, 1 minute. I'll stop this and then I'll share once again. Now I think this is clear. Is this
Yes,
clear?
ma'am.
Yeah. Now, yes, 5 different techniques we have studied and how to select those process or else methods. So that depends upon the corresponding principle. Okay. So now coming to the third process. So students, at the end of the second process, so what you have? Once again, it is a ore only. Okay, ore. You don't have any metal in this in its pure form. 1 minute. Students, now you have ore. Okay, it contains some amount of impurity. Okay, it contains some amount of impurity, but a maximum amount of impurities are removed using the second process. So the third process is nothing but isolation of metal. Okay, third process is nothing but isolation of metal. Students, so what you have to do? Isolation of metal means you have to extract metal, correct? So you have to separate metal in from that ore. So there are 2 techniques, students. You either first you have to follow the procedure first procedure, then you follow the second procedure. So what is the first procedure? So it is not easy to extract metal from the ore. So first what you have to do? So first convert this metal to corresponding metal oxide. Okay, convert that metal into metal oxide. So that is the first process. And second main process is under this third main. Second process is nothing but the reduction process. Okay, so reduction process. Now, in this metal to metal oxide conversion, once again, you have 2 techniques. So that is nothing but a calcination technique. What do you mean by calcination? So heating in the absence or else in the limited supply of oxygen. Is this clear? Okay. Then one more technique you have. So that is nothing but a roasting process. So roasting technique means you have to heat the ore in the excess amount of oxygen. Excess amount of oxygen. Is this clear, students? These two technique. Then coming to the reduction part, students, you need to add a reducing agent here. Okay, add a reducing agent. So students, reduction in the sense you have to take this metal oxide which is obtained here, okay, from the, so A step means third main A. You take this metal oxide, add a reducing agent. Yes, Chirag? No?
Yes,
Any
ma'am.
doubt? Any doubt?
No doubt, ma'am.
Okay. So you take this metal oxide and from that metal oxide you have to extract metal. How? By the addition of a reducing agent. Okay, by the addition of a reducing agent. So now we'll list out, okay, 1 minute. Yes, Anika. Anika, na? Who is asked that question? Shashanka, yes. Shashank MN, yes, there is a webinar today that is at 5 p.m. You want to attend that? Huh? Yeah. If you attend that, then you will miss this class. I know you are interested. Yeah. But at a 6:45 there is a quiz. Okay. So of first chapter, sorry, not first, second chapter, previous chapter. Okay. Now you just concentrate on this third process. You have to extract metal from metal oxide by the addition, by adding reducing agent. Is this clear? So now students will concentrate on the fourth step. So fourth step is nothing but at the end of the third main you have metal, right? You have metal. So fourth step is nothing but a refining. Okay. So you have to do purification because it may contain small amount of impurity. This metal may contain small amount of impurity. So therefore go for purification technique. Is this clear? Students, here I want to concentrate on two things. Okay. So reduction process as well as the refining process. Okay. So now you just concentrate on the reduction process. Okay. So reduction process. What I mean by reduction here? Okay, reduction is nothing but you have different types of definitions, students, whether my means class is fast, very fast.
No,
Are you
ma'am.
able to understand? Are you able to understand? Okay.
Yes.
Yes, students, coming to the reduction process, actually here I have to extract the metal from this metal oxide, okay, from metal oxide by the addition of a reducing agent. So what are the common reducing agents which are used in this metallurgical process? Okay. So reducing agents which are used in the metallurgy. Okay, reducing agents in metallurgy. So usually you can use either carbon as a reducing agent or else carbon monoxide as a reducing agent or else other metal as a reducing agent. Okay. So when to use this carbon, when to use that carbon monoxide and when to use that other metal as a reducing agent. Did I explain that? Ellingham diagram, did I explain anything? Ellingham
Yes,
diagram?
ma'am. Yes, ma'am.
Whether it is completely done, the completely in the sense
Yes, ma'am.
delta G naught value must be less,
Yes,
okay,
ma'am.
and there must be a phase transfer. If there is a bending in the graph, then it indicates a phase transformation, and if there is a intercross, then only you can consider that metal as a reducing agent that we have discussed, right? Okay. So then just glance this. Students, metal oxide as well as metal is there. I have to extract metal oxide, metal from metal oxide. I can use carbon as a reducing agent or else carbon monoxide as a reducing agent or else other metal can be used as a reducing agent. So this particular process is called pyrometallurgy. Okay. So this process is called pyrometallurgy. Pyrometallurgy means extraction of metal from metal oxide by using any reducing agent. It may be carbon or else a carbon monoxide or else other metal as a reducing agent. You can use these three. Is this clear? Okay. So students, one more situation is there. This is one situation. One more situation is there. Students, I can extract metal from metal oxide by the addition of carbon as a reducing agent. Okay, carbon as a reducing agent. So this particular process is called smelting. Is this clear, students? If I use carbon as a reducing agent, then that process is called smelting. Is this clear? Okay. Students, now today we'll discuss about the fourth main process. Okay. Fourth of main process is nothing but, 1 minute. Fourth main process is nothing but a refining. Okay, a refining process. See, there are different techniques. Once again, it depends upon the principle. Okay, the nature of the element that you have to purify, or else the corresponding principle. According to the principle, or else according to the nature of the element or else compound, you can decide the particular. You can select the particular process. Students, in this case of refining, in your textbook, 3 types of process is given. So first one is a distillation. Distillation. I think this is not discussed. You just write down everything. Students, before that, why this refining process is to be used or it is to be done? So after extraction of, you just concentrate on the slide. See, this is reduction. Reduction is nothing but a third metallurgical process in this, that is second step. So you will get a metal. Once again, this metal is not pure. Okay, it is not pure. It may contain small amount of impurity. Okay, so in gold, see, while purchasing gold, if I add small amount of impurity, will you accept it? No. Correct? I have to remove that impurity also. Small amount. If it is very small, then also I have to remove that. Okay, so remove this small amount of impurity. How to remove this? Go for refining technique. Okay, based on the impurity, nature of the impurity, or else based on the nature of the metal, you select different techniques. Distillation process is the first one of the refining technique. Okay, so here you need to give importance for the state of the physical state is very important. Physical state of the ore. Ore means of, or else you consider it as a metal now, because at the end of the third step, metal is there with us. Okay, extracted. So the liquid state, you have to give importance for liquid state. Here, the boiling point of, you just write, this is a principle, okay? So principle, boiling point of metal is less. Boiling point of metal is less and boiling point of impurity is more. That is the meaning, okay? Or else this is the principle of this process. Students, what is the setup? It is not there. You just, if you want, you can draw, or else you can escape. You just concentrate on the explanation. Students, this is a round bottom flask. Okay, so side stand and all, or you have to draw. Okay, if you want, you have to draw. Otherwise, so that round bottom flask is not a, you can't fix like that. So this, there is a stand, etc. Okay, clamp, etc. Then you close this mouth. It is a condensed system, or else your condensed system means it is, you consider it as a closed system. There are 3 types of system, students: open system, closed system, and isolated system. Open system means everything can exchange, energy can exchange, or else surrounding, energy can be exchanged between the system as well as the surrounding. Okay, then closed system means there is no exchange, energy can exchange, matter cannot exchange. Okay, isolated means matter or else energy, so both are not, means you can't exchange those two between the system as well as the surrounding. Is this clear? System means, for example, if I consider this classroom as a system, corridor is the surrounding. Okay, system plus surrounding is nothing but environment. Okay, is this clear? So if I open all these windows as well as door, then it becomes an example for open system. If I close, okay, open system, so at that time I can throw some students out from either from the window or else from the door, correct? So matter can be exchanged. And if you shout here, that energy can be exchanged, correct? Matter can be exchanged, energy can be exchanged in case of open system. Is this clear? Now you close all these windows as well as door. At that time I can't throw any student out, correct? So matter cannot be exchanged. But can I shout? Yes, I can shout. Some other can hear, correct? Energy can be exchanged. Okay. So energy can be exchanged. That isn't in case of closed system. Matter as well as energy both can be exchanged between the system as well as surrounding in case of open system. In case of closed system, only energy can be exchanged, matter cannot be. And what about isolated? Isolated means you completely cover something. Okay, so 1 minute. See, now there is a pen. So I'll cover like this. Can you see this pen now? No. Matter cannot be exchanged. If I cover like this, okay, so you can't see, that is matter cannot be exchanged. Even energy cannot be exchanged between the system as well as surrounding. It's completely separate, okay. Isolated means completely separate, okay. Is this clear? Three types of systems are there. So now you take a closed system, closed container, and here you take a metal. Here you have to take a metal which contains small amount of impurity. Okay, which contains small amount of impurity. So this is the refining process. So now students, there is a pipe here. Side pipe is there. Okay, tube, side tube is there. So you connect a condensed system for this. Say that you can see you're heating, right? At that time, this glass may blast. So therefore, you have to circulate, or else you have to give one water connection. Okay. So water circulation must be there. So that temperature will be maintained. Room temperature will be maintained. So now connect one beaker, a pipe, and then keep one beaker here. Once again, stand is required here. Okay. Students, heat this one. Heat this. What is that? Metal as well as small amount of impurity. Students, what is the principle now? What is the principle? Metal whose boiling point is less. You have to select a metal in such a way that, or else compound in such a way that its boiling point is less. Is this clear? Yes. Boiling point is less means, students, you heat this one here, from here. So which one will melt first? Here. Metal will melt first, correct? Metal will melt first, sorry, not melting, boiling. Metal will boil first. Is this clear? Because its boiling point is less. So now students, this metal will melt from solid. Okay, melting process is nothing but conversion from solid to liquid. Yes, that will evaporate and it will be collected here. What about the temperature in this case? In this area, temperature is less, correct? You are heating here, right? Here temperature is more. In this bottom portion, temperature is more. So this portion, temperature is less. Is this clear? So now what happens? Those droplets, they combine with each other and then they will fall. When they fall, this side tube is there, right? So that will come here and then that liquid will be collected here in this beaker. So now tell me, what is this? What is that, student?
Pure metal.
It is a pure metal. Okay, pure metal. It is a pure metal. Is this clear, students? And what about this impurity? Impurity will stay here because its boiling point is more. Is this clear? Is this clear? This is a distillation process. Is this clear, students? Any confusion in this distillation process? No. Students, here in the distillation process, the physical state of the metal is nothing but liquid. So if you have solid system, then what you have to do? Go for liquefaction process. Okay, go for liquefaction process. Here you need to give importance for melting point. Okay, melting point of metal is less. That is not, this is the principle. Okay, so then it is understood that impurity, its boiling, melting point is more. Students, keep your videos on. Okay, so now how to carry out this reaction, students? The structure setup will be like this. So this substance you take a, see what is this, students? Yes, you have to heat this one. So students, this is nothing but a metal which contains small amount of impurity. Okay, metal which contains small amount of impurity. And then what you have to do, students? Here you have to heat it, heat this one. Then what happens? So these are all the solid substance, right? So what is the what happens? Melting takes place. Okay, it melts. But according to the principle, the melting point of metal is less. Which one will melt first then? Metal, correct? Metal will melt first and it will be, so you keep one beaker here. Okay, so metal will be melt first and it will be collected here. So here what you are going to get in this case, so this is nothing but pure metal. And what about impurity? Students, impurity, its melting point is more. Yes. Students, 1 minute. Distillation process is only for the liquid metal, or else any metal you can take, but you have to convert that one into liquid state. So after that you can purify it. Okay. Then, so here you take a metal which contains small amount of impurity, heat it. At that time, the melting point of uh, 1 minute. Yes, melting point of this metal is less. Okay, melting point of metal is less. So sorry, boiling point of metal is less. So therefore, it will boil first and it will be collected here. Those droplets will be collected here. But here temperature is less, so correct, temperature is less, so they combine with each other, condensation process. Okay, it will be collected here in the beaker. So this is nothing but a pure metal. And what about impurity? Impurity will remain here. Okay, so if the physical state of the substance is a solid, okay, if the physical state of the substance is solid, then go for liquefaction process. So according to this liquefaction process, melting point of metal must be less, low. Is this clear? Melting point of a metal is less. That means melting point of impurity is more. So now this is the setup to do this liquefaction process. So students, you take metal which contains small amount of impurity and heat it. So here the melting point of metal is less. So therefore it will melt first and it will flow like this. Melt means what? It will be converted to liquid form, correct? So it will flow here and you collect those metals here. So in this beaker you can collect this metal, okay, pure metal. Then what about the impurity? Impurity will stay here. Okay, so in the slope, this is nothing but impurity, so that you can separate impurity from metal. Okay, so it should not, it's, you have to restrict, you must restrict the melting point of this metal. If it is very nearer to this metal, then you can't take this liquefaction process for the purification technique. You have to go for other technique. Is this clear? Otherwise that will be mixed with the metal once again. So at that time, if you do this liquefaction process also, then it is waste, correct? Yes. Students, is there any doubt in the liquefaction? Nina, is it clear?
Clear.
Nihad, you have asked to, yeah, repeat this equation. Is it clear?
Clear, ma'am.
So now the third refining process is nothing but electrolytic refining. Third refining process is nothing but electrolytic. Students, to explain this electrolytic, so yeah, since I have already explained galvanic cell, do you remember that? Do you remember? No. 1 minute. Give me 1 minute. Yeah, the third process is nothing but electrolytic. Okay, electrolytic process. Third one. So to explain this, Mithul, to explain this, I need some concept from galvanic cell. I think it is already known to you. Correct, electrolysis. Mithul, are you discussing or are you explaining the galvanic cell process? No? Mithul? Mithul? Mithul, I'm asking some question. Yes, explain. Mithil, explain this in detail. Yes, students. Coming to this galvanic cell, okay, coming to the galvanic cell. Yes, you don't know, I know, because you were talking. Yes. Students, coming to this electrolytic process, if we need to concentrate on the electrodes. So electrode, positive electrode, oxidation process, negative electrode, negative reduction process, everything we have seen in galvanic cell, okay, in first chapter. So even though it is not there, so we have explained, correct? So now students, here let me concentrate on the two topics here. First, electrolytic means I will concentrate on the electrolyte. So electrolyte is actually a liquid, okay? What do you mean by electrolyte? You see, there are two concepts. One is electrolyte and one more is a non-electrolyte. Write all these points if you want. Electrolyte is the one, it's a liquid, okay, solution which conduct electricity. Solution which conduct electricity, okay. Electrolyte is the one which conduct electricity. How? By the movement of ion. By the movement of, or else you have to concentrate on the movement of, or else yes, mobility of ions. Ions may be positive or else negative, okay. Positive ion means cation or else anion. Now, for example, you consider HCl. HCl is an electrolyte. HCl solution, if you prepare, it is an electrolyte. Because you can study the electricity, it conduct electricity. HCl solution conduct electricity because you can split this into H plus ion as well as Cl minus ion, okay. You can prepare ions, cations as well as anions. In the same way, you can take even base, sodium hydroxide. It also gives Na plus ion as well as OH minus ion. So that means whenever you have ions, that will belongs to this electrolyte section. Is this clear? Now, you can also take a salt as an example under this. It also gives Na plus ion as well as Cl minus ion. So, whenever you have positive ion as well as negative ion, it conduct electricity. Okay. So, then what do you mean by non-electrolyte? So, you just write a solution. What may be the definition? Which does not conduct electricity. Okay, solution which does not conduct electricity is called a non-electrolyte. That means here ions are not there. Okay, ions are not there, absence of ions. You can't split that molecule into positive ion as well as negative ion. For example, you consider the, yes, urea. What is the formula of urea? NH2CO NH2 is the formula of, sorry, what is the urea formula? Yeah, correct. NH2CO, NH2. So can you split this into some positive ion as well as some negative ion? No. Okay. You consider an example of glucose. Okay. C6H12O6. Can you split this one into positive as well as some negative? No. So that therefore, if you are not able to split some substance or else a solution into positive as well as negative, if you are not able to split, then it does not conduct. Okay, is this clear? So now once again so therefore we are not interested in the non-electrolyte, so we'll concentrate on the electrolyte now. In electrolyte also you have two classification. One is nothing but a strong electrolyte. First one is nothing but a strong electrolyte, and the second one is nothing but a weak electrolyte. Strong electrolyte as well as weak electrolyte. Students, so what I mean by strong electrolyte? Strong electrolyte is the one which dissociates completely. Okay, so which dissociates means splits. Okay, completely. Strong electrolyte is the one which dissociates completely. If you take an example for the strong electrolyte, you can take an example of strong acids. For this, examples are HCl, H2SO4, HNO3, etc. You just take this example, write this equation. The moment you take this HCl and then if you insert a electrode and then if you pass electric current, then it completely dissociates to give H plus ion as well as Cl minus ion. One minute. Yes, students. Now, complete dissociation means you have to use this arrow mark, okay? So, forward direction, because whenever you insert electrode, complete splitting takes place and you are going to get a complete dissociated amount of, or else a pattern that is nothing but H plus, some positive ion as well as some negative ions, okay? Yes, students. 1 minute. Now students, take another example that is nothing but a strong base. Strong bases is it also contains ions. Okay, so example for this is nothing but NaOH as well as KOH. Now you take a sodium hydroxide and insert electrodes and apply energy. You can write or else you can split that into two parts, that is Na plus as well as OH minus ion. And similarly, you can take even a strong salt as an example for this. Examples are nothing but NaCl, KCl, etc. So you take this NaCl and then apply energy, means energy in the sense dip two electrodes, and you can get Na plus as well as Cl minus ion. So this is in terms of strong electrolyte, in case of strong electrolyte. So then what do you mean by weak electrolyte? Weak electrolyte is the one where dissociation is partial, means incomplete dissociation takes place. Dissociation is partial, or else a dissociation or else a splitting rate is there, right? So that rate or else a speed is very, very less. Splitting rate is very, very less. So what are the examples for this? So that is nothing but, we'll give one example. You just take the same in terms of acid. A strong acid is written under this strong electrolyte. Here you write weak acids. Example for weak acid, there are so many. Let me take only acetic acid. So now you write the reaction, students, even though it is a weak, a partial dissociation takes place, but you are able to produce a cation as well as anion. Students, for the partial dissociation, I am using this arrow mark. Okay, so what is the meaning here? One is nothing but equilibrium. You can take it as equilibrium, or else rate of forward is equal to rate of backward. That is the meaning. So you split this one, you will get it as a CH3COO minus as well as EH plus. Okay, EH plus. Over. Then students, similar to the weak acid, you have a weak bases also. Weak bases. For example, ammonium hydroxide is a weak base. Okay, same thing, but you are able to prepare ions here, that is NH4 plus as well as OH minus ion. And the last one is a weak salts. Weak salts. So once again, you take an example of ammonium chloride, but you are able to prepare cation as well as anion, that is NH4 plus as well as Cl minus ion. So whenever you are able to prepare positive as well as negative ion, then those two ions are important for conductance. Okay, is this clear, students? Electrolyte and a strong electrolyte, weak electrolyte, its classification, examples, everything clear, right? Is there any doubt in this? Yes. Students are coming to this electrolytic refining. So my topic is now this one, refining process, electrolytic refining. Students, give me 1 minute time. See, coming to this electrolyte or electrolytic refining, here principle is like this, students. Principle is like this. You have to take impure metal strip as anode, and strip of same metal in its pure form is taken as cathode. Is taken as cathode. Is this clear, students? So the principle of electrolytic refining is like this. You have to take two electrodes. Okay, you have to take two electrodes. One electrode must contain impurity, and one more electrode must be pure. But those two electrodes are made up of same metal. Is this clear? One is impurity and one more is pure form of same metal. So now students, using this electrolytic refining technique, you can refine either copper or else zinc using this method. Okay. So now let me write some reaction related to anode as we have discussed earlier in the galvanic cell. At anode always oxidation process takes place, correct? So now for example, if I take a metal, oxidation is nothing but a metal N plus N number of electrons are released, correct? Oxidation means what? See, if nothing is written, then if metal is there in the pure form, so then the oxidation state is 0. If it is written as N plus, in its oxidation state is N plus, it means always 0 as well as N plus. If you consider N plus is always greater than 0, correct? So this process is nothing but oxidation. So this happens at anode. So next you consider cathode. In cathode, okay, reduction process takes place. So that means you write it as Mn plus, plus it gains N number of electrons, and you are going to get M, metal, pure form. Anish, shall I remove you? Ashay, Medansh, Muralidhar, Shashank V, Saujanya, Pratyusha. Yes, students, and now this type of reaction is called a reduction process. So there where electrons are gained. Okay. Yes, Sumedh, which slide you want? This one or else this one? This one? This one. Next is this one. Yes, you unmute and then tell me which, yeah, over, over, huh? Yes, so this was the first slide related to electrolytic. This is nothing but the second slide. Yes, students. So now at cathode reduction process takes place and then at anode oxidation process takes place. This is nothing but the oxidation process and this is nothing but a reduction process. Now these two reactions are called redox reactions, and those two electrodes are there, right? That is cathode as well as anode. These two electrodes are called redox couples. Okay, redox couples. In one electrode oxidation takes place and in another electrode reduction takes place. Okay, so now students, the explanation or else a purification step is like this. Students, you would consider one beaker. In this you take electrolyte. Okay, electrolyte is required for us. So electrolyte is the one which conduct electricity because of the movement of ions. So now let me take an example of refining of copper. Okay, so what type of electrolyte I have to take? In that electrolyte, copper term must be there. Okay, so let me take copper sulfate as an electrolyte. Copper sulfate. Students, you split that copper sulfate, you are going to get Cu2 plus as well as SO42 minus. So that means in the electrolyte, copper is present in copper 2 plus form. Is this clear? In copper sulfate, which is there in this liquid solution, that is, sorry, liquid phase, that is called electrolyte. So in case of electrolyte, copper is there in copper 2 plus form. And now students, dip one electrode here. Okay, it must be straight. Okay, yes. Then dip one more electrode here. It must dip also. Yes. Now students, let me write this as a positive and this as a negative. Students, in galvanic cell, anode was negative, cathode was positive. Is this clear? We have explained why anode is negative. That is because of electrode-electrolyte interface. Is this clear? Do you remember? Yes. So with respect to electrode, this electrolyte is negative, or else with respect to electrolyte, this may be negative. So based on that, we have given the sign. But now I'm concentrating on the electrolytic cell, students. Electrolytic. This here, anode and cathode means it is your normal anode and cathode. Okay. Normally anode is positive and cathode is negative. Is this clear? Galvanic means what, students? I have to couple two different metals. That is called galvanic. But now in this experiment or in the electrolytic refining of copper, I will connect it to electrode, but these two electrodes are made up of same metal. Is this clear? So it is not a galvanic, it is a electrolytic. Two types of cells are there. Okay. If electrochemistry notes is there, then just glance it. So students, this, okay, let me write it as an anode and let me write this as a cathode. Don't make confusion, students. There is a difference in the charge between the electrolytic cell as well as in the galvanic cell. Connect it to the external circuit. So whenever you connect this one into the external circuit, the current movement takes place. So students, now you just concentrate on this video. I have two electrodes here. One is black and one more is white. Okay, you concentrate on this top. Students, imagine this black is a anode. Yes, this one, sorry. This one is anode and this one is cathode. This one is anode and this one is cathode. Where is this anode? Anode is kept on the left hand side, students. It is a left hand side. Okay, and cathode is kept on the right hand side. You connect these two to the external circuit. Connect these two to the external circuit. Then current movement takes place, or else electrolyte will split. dissociation of electrolyte takes place. Electrolysis, that process is called electrolysis. Okay. Now students, here, okay, black color is there, right? So yeah, now you just concentrate on the principal part. Always students, I have to select anode in such a way that this anode must be impure copper rod. For example, in the purification of copper, okay, impure copper rod. What about this cathode? Cathode is nothing but a pure copper rod. Is this clear? Okay, so that is nothing but it's a principle. Impure metal strip is to be taken as anode, and strip of same metal in its pure form is to be considered as cathode. Is this clear? Yes. One minute. Students, and now what is this anode? Anode is nothing but impure form. Students, you concentrate on this pen where a cap is black. Imagine this is the impurity. You know what happens when you connect this one into the external circuit? Electrolysis takes place. Something will fall from here to the electrolyte. Is this clear? So what was the process? You just concentrate on the process which is written on the anodic side. Previous general equation I have written. So that is nothing but M will be converted to Mn plus. Oxidation process. Oxidation means what, students? It is a removal of electron, correct? Oxidation is nothing but removal of electron. Students, now something will fall from here to the electrolyte. Imagine this is the electrolyte. So now one more electrode is there here. What is this? This is the pure form, metal in its pure form. Okay. So now something which is collected here. So from this, 1 minute, this is a impure. From this something is collected here. So what is this? This is anode. So from this anode something is collected in this electrolyte, and that part is called anode mud. Is this clear? Because it came from anode and it is unwanted material. Impurity is there. Okay. It's actually not unwanted. This is not unwanted material. Okay. But you imagine like this. The mud term is there, right? Mud term is related to the impurity. Why? Because you took this impure copper rod. Okay. This anode is made up of impure. Then students, you have a pure form. Okay, so cathode is there, so which is made up of copper, but it is in its pure form. So now the anode mud is there, right? So something is collected in the electrolyte. Okay, so that will deposit here in the pure form, means in the cathode. Is this clear? Is this clear? Now you disconnect this external circuit and you are able to prepare, or else you are able to get a pure form of copper. This is the electrolytic refining process. You can apply this process for copper as well as zinc. Is this clear? Students, I will explain here. Students, here impurity is there, metal is there, as well as small amount of impurity is there. Here only metal is there. So here something will fall here. So what is that actually? Is this impurity or else metal? Huh? Metal or else impurity? You just concentrate on the reaction here. Yes, what is this? Can you tell me? Yes, Anika, tell me. Is this metal or else impurity? Is this metal? See, strip is there. Okay, strip is there here like this. Impure form. Something will fall. Okay, here metal is there, impurity is there. Something will fall here. So what is that actually? And that will be deposited in the cathode and will get a pure form. Means what is that? This is a metal. Okay, it is a metal, not impurity. Okay, impurity will remain as it is. Okay, so metal will fall here. So when, see here metal is there in zero charge. When it fall here, then it will carry Mn plus charge. For example, what is this metal? This metal is nothing but copper. What is this electrolyte, students? Electrolyte is nothing but copper sulfate. Split this copper sulfate. Copper is there in the copper 2 plus form. Correct? So that means Cu, okay, let me write it as Cu. So it will fall here and it will be converted to Cu2 plus ion. Is this clear? It will deposit here. It will deposit here. So this deposition is called anode mud because this is the impurity which is found in this electrolyte. Okay, electrolyte means it is a rich in Cu2 plus as well as SO4 2 minus. But now something extra came from the anodic part. So since it is collected from anode, so this mud is called anodic mud. Is this clear?
Ma'am,
Okay.
why mud, ma'am? It is pure metal, ma'am.
Yeah, it is pure metal, but metal is there in its oxidized form. So I don't want that oxidized form. Okay, I need to get, see, what is the extraction? Extraction means I have to get a pure metal. Okay, so for example, if you get a gold in an oxidized form, it may react with some other metal, or else you take any other metal. If you buy that it in the oxidized form, so it is not a stable one. It reacts with, if some electron is moving somewhere around that, so it gains that electron and it will be converted to the pure metal form, correct? Pure metal. Is this clear? So therefore, so I see here, here copper was there. So when it is under, when it so what is that process? Oxidation process. After oxidation, it will fall here to the electrolyte. Here it will be in the form of Cu2 plus. Okay, so process is not process will continue here, students. So this is a anode mud. From here something will deposit on this cathode, will deposit in the cathode. Is this clear? Is this clear? So that is nothing but, see, the process is like this. Two rods are there. Something will fall to the electrolyte. Then from here, this will deposit here. You stop this external connection. So you remove this connection. So at that time, what happens? You can get a pure metal in this cathode. Okay. So those, see, already that cathode, 1 minute, already that cathode contains a pure metal only, pure metal. But this anode was there, right? So from here metal will fall here, right? That metal will be deposited on this cathode. Is this clear? Okay, so now you stop this connection. So remove this cathode. Cathode is rich in copper, rich in copper. Is this clear?
Excuse
So
me,
this is
ma'am.
the 1 minute. This is the electrolytic refining technique. Yes, tell me.
Why does the oxidized metal from the anode fall into the solution, and why do you need a copper sulfate solution itself?
Yeah. See, if I want to, 1 minute. Shall I rub all those points? All these things? Okay, I will rub this one, right? See, Muralidhar, do you remember anything about the galvanic cell and its process, etc.?
Little bit, ma'am.
Okay, so there is see, these are all belongs to the electrochemistry chapter. Okay, these concepts are from electrochemistry. There are some certain rules, observations. So there is one table also. Okay, table in the sense electrochemical series is there. So they have given particular reaction. So always here in electrochemistry, you can observe redox reaction. What do you mean by redox reaction? Redox reaction is nothing but there are two types. One is reduction and one more is nothing but oxidation. So always reduction as well as oxidation takes place under redox reaction, and that can be observed during electrolysis process. So now students, usually there are two types. See, 1 minute. Electrolysis process, if you want to do this process, you have to consider at least two electrodes. You have to consider electrodes. At least two electrodes you have to consider. If you combine two electrodes, so one is nothing but anode, okay, so which is actually positive in general, okay, and one more is nothing but a cathode. In general, it is negative, okay. So if you connect these two, you are able to prepare or else create one cell. One cell means there are two half reactions or else half cell. One cell, okay, so I will write like this. One cell means there are two electrodes. One is positive and one more is negative. Okay, students, based on the electrochemical series, means someone did this experiment. Based on this electrochemical series, I can say that, so there is a generalization, okay. I can say that at anode always oxidation takes place. Okay, oxidation means what? Okay, so before that, cathode, one more is nothing but cathode. At cathode always a reduction reaction takes place. Muradhar, is this clear? Okay, so this is a
Yes, ma'am.
observation, general observation. Students, so what do you mean by oxidation? Okay, oxidation means, you know, it is nothing but a removal of electron. Minus electron means it is a removal of electron. Is this clear? Now students, and 1 minute, reduction is nothing but addition. Reduction is nothing but addition of electron. Students, here in oxidation, number increases. Number increases. Okay, oxidate number in the sense it's actually oxidation number increases. And in case of reduction, oxidation number decreases. Okay, oxidation number decreases. Now students, if any metal is there in its free form, then its oxidation state is always 0. Okay, if metal is there in its free form, okay, so they don't, for example, copper alone, or else silver alone, gold alone, okay, at that time its oxidation state is 0, it is free. Now if you remove one electron from that, then the oxidation state is +1. If you remove 2 electrons from that, then the oxidation state is +2. Okay, is this clear? Is this clear? How to
Yes, ma'am.
decide oxidation state and all? Yes. Students, now you write the electronic configuration of copper. So it is actually 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9 actual configuration. Okay, but you know the completely filled electronic configuration is highly stable, so therefore you will shift one electron to that side, correct? But actually, naturally, this is the actual configuration. Students, here what do you mean by oxidation? Oxidation means a removal of valence electrons, correct? Which one is the valence shell here? Valence shell means the last bench, or else the last shell here. So that is nothing but the 4, correct? So 4. So here it shows, you can remove 2 electrons from this system. So it shows a +2 oxidation state. So now if you write the general electronic configuration of 3D series, almost all 3D elements shows +2 oxidation state. Is this clear? Is this clear? So therefore, so this is zinc, or else you consider even zinc. Okay, zinc, same electronic configuration. Okay, I can write it as a argon, and you will get 4s2 3d10. 4s2 3d10. What is the minimum oxidation state in this case? Minimum oxidation state means minimum amount of energy required to remove the valence electrons. How many valence electrons are there here? 2. So apply certain amount of energy, remove this. So that means it shows a +2 oxidation state. Is this clear? Yes. Therefore, in case of copper as well as in case of zinc, it is easy to remove 2 electrons which are there in the valence shell. Till here, any doubt?
No, ma'am.
Okay. So now students, I have taken impure rod. 1 minute. So what is this? This is a impure copper rod. Okay. What is oxidation? Along impure copper rod means along with this copper, small amount of impurity is there. Okay. So now students, you apply energy to this. Now before that, what is the oxidation state of this copper? This copper oxidation state is 0 because it is there in its free form. Correct? It is not mixed with something else. Something else in the sense, maybe it may be in the form of oxide or else in the form of sulfide, etc. But what we did a certain experiment. Students, you just concentrate here. We did one minute. Yeah, we did a reduction process here. We have added reducing agent and we have converted that corresponding oxide to its pure form. So you take this metal now, but it contains, unfortunately, it contains small amount of impurity. So you take that metal here. Okay. So copper oxidation state is 0. Now you connect this. Okay, there are two rods. Okay, one is cathode and one more is anode. Connect it to the external circuit. So what happens? Current passes, right? Correct. Splitting takes place. So since copper is there in its pure form, okay, pure form, it readily donate electrons. Is this clear? Muralidhar, is this clear?
Yes.
It donate its electron means one copper, how much it can it can donate one electron, okay, or else 2 electron, or else it can also donate a 3 electron. But there is one more chapter, D block. So if you, or else you know the electronic configuration, periodic properties done, right? So you write the electronic configuration of 3D. So if you write the electronic configuration of 3D series, then the last shell contains 2 electrons. So therefore common oxidation state of all 3D elements, copper comes under 3D. Okay, so that is +2. So it will donate 2 electron to attain +2 oxidation state. Is this clear, Muralidhar? So
Yes.
therefore copper will be converted to Cu2 plus form in one side, and in another side, since you have taken, see, this is a anode, right? And the cathode is there here. Cathode, this is actually pure copper. Okay, so copper oxidation state, once again it is 0 here, but these two are, see, it is dipped in copper sulfate. Why copper sulfate? So always you have to take a particular solution. Particular solution means it must contain common ion. Is this clear? If you take zinc rod, then you have to take a zinc sulfate solution. If you consider iron rod, then you have to consider copper, iron sulfate solution. If you consider copper rod, then you have to take a copper sulfate solution. So that is nothing but the common ion must be there in the rod as well as in the electrolyte. Is this clear? Therefore, we have to take copper sulfate here. Muralidhar, is this clear?
Yes.
Okay. So there is a, see, students, one more concept is there. Why we have to take a common ion? So there is one solubility concept is there. Okay, that will discuss in next year at the equilibrium chapter. Students, now, yeah, here copper was there in the free form. So now these two are dipped in copper sulfate solution. Correct? You split this one. How to write this formula? So you know how to write the formula. So some positive ion or else some negative ion. So what you have to do, how to write the formula? You multiply like this, cross multiplication. What is the oxidation state of copper? Copper oxidation state is always +2. And what is the oxidation state of sulfate? Or what is the charge of sulfate? Charge of sulfate is -2. So multiply this by here, by 2, here by 2. So the sulfate formula is, copper sulfate formula is a CuSO4. If you consider a common electrolyte, which contains a common ion, then the movement of ion will be easy. Transfer of electron will be easy. Redox reaction rate will be more. Okay, so now you connect this to the external circuit, then current passes and then something will fall here, from here to here, correct? So this contains copper as well as small amount of impurity. So now copper was there in the free state, here it is 0, oxidation state is 0. So it will fall here, right? What is the charge of copper here? You concentrate on this copper sulfate. Copper sulfate charge is nothing but a Cu2 plus, correct? So Cu2 to Cu2 plus means, 1 minute, conversion from Cu to Cu2 plus means what is this, students? oxidation number increases, correct? Oxidation number increases means from 0 to 2 plus. So this process is called oxidation process. Okay, oxidation process. So 2 plus is there. During oxidation, okay, let me write here. During oxidation, what happens, students? Electrons are released. So write 2 electrons to the product side because it is released. So now this is the reaction which takes place at anode. Okay, so now I have to deposit some pure metal in the cathodic part. So Cu2 plus, which is there here, it gains 2 electrons which are shifted from here, and it will deposit to this rod, or else it is reduced. When Cu2 plus, see at the cathode, what type of reaction takes place? Actually, Cu2 plus, which are there in the electrolyte, gains 2 electrons which are released from the anode, and it will be reduced to Cu. Okay, then now charge reduces from 2 plus to 0. Okay, so this process is nothing but a reduction, and this copper will deposit in the cathode. Is this clear?
So it is the electrons that is released and not the Cu2 plus itself from the anode.
Yeah, it's Cu2 plus was there in the electrolyte part, right? So it gains these electrons and get reduced, and it will be deposited on the cathode. Is this clear?
So what the anode releases is the electrons.
Yes.
Okay.
Okay, so
Thank you.
anode is there, right? So here copper is there. Okay, small amount of impurity is there. So leave this impurity. So at the end you can get only impurity in this case. Okay, so this will be transferred to Cu2 plus form. At the same time, 2 electrons are released. Cu2 plus conversion means 2 electrons are automatically released, correct? So this Cu2 plus gains, it will gain this this Cu2 plus, which is there in the electrolyte. So that gains 2 electrons which are produced by anode and gets reduced. That reduced form will deposit in the another electrode. Is this clear?
Excuse me, ma'am.
Yes.
In the solution itself, it gets reduced to Cu like normal Cu.
All are same. All are same. Okay, you can't distinguish. So yeah, your doubt is like this, right? So in the electrolyte, Cu2 plus is there already. Cu2 plus is there, and then SO4 2 minus ion is there, correct? But here some copper metal will be there, right? When you connect it to the external circuit, okay, external circuit, this will be converted to Cu2 plus, correct? So now all Cu2 plus are same, either from this or else from this electrolyte, all are same. Okay, so this is once again a continuous process. This process will continue till how much see how long you're applying this energy, external energy, till there this will continue. Okay, yes.
Excuse me, ma'am.
Yes.
Ma'am, can we use that electrolytic solution again in any other process?
Which one? Where?
Ma'am, CuSO4.
Electrolyte.
Can we use that CuSO4 again?
Yes, sir. This is you again where to another process.
Yes, ma'am. Another process.
Sometime what happens, there are some movement, so at that time the color changes takes place, so you can't use sometime. Okay, so we'll show here like this, right? But its setup is something different. You have one chamber. Okay, so imagine one copper vessel, imagine like that, and there is a porous pot, so that is of white color. Okay, then you take a copper sulfate solution. It's actually blue color, right? Yes. Then you consider copper rod, dip one copper rod here, and then one more connection will be there in the copper vessel only. So you can observe that connection here. Okay, connect these to the external circuit. Then you can get sometime what happens. There is a how to represent. See, imagine this is a bowl, copper vessel, and this is a porous pot here, white color. One part will be there, and inside that also you have to take you have to dip some this one electrode, okay, and you have to take a solution there, and sometime an ion exchange takes place, some not sometime, it's always, okay, ion exchange takes place between these two. At that time the color fading you can observe, uh, means it's a color bright intensity will be there, right, that can be reduced. So at that time you can't use that copper sulfate once again to the other experiment. If you, for example, imagine like this, so 1 molar copper sulfate solution is taken, imagine like that, 1 molar, and it color intensity, it has its own color intensity, correct? 1 minute, correct? What happened to this? Okay. That copper sulfate is a blue color, okay, so there will be a slight fade in color. So if you take 1 molar, it's after reaction its concentration may vary, it may increase or else it may decrease, that depends upon the practical, okay, experiment. Is this clear, Kitten? So
Yes, ma'am.
it will never, this strength will never remains a change, you can see the color. So in second year that type of experiment is there, okay, in the electrochemistry.
Excuse me, ma'am.
Hi, yes, tell me.
Ma'am, why can't impure metals to be like connected to cathode and then undergo oxidation, then the reduced form go to anode, ma'am?
Yeah, you are asking some reverse reaction, correct? Reverse reaction. Yes, students, that is also possible, but you have to concentrate on the oxidation potential. See, yes, if I will give some value, imagine I will give some value for some reaction, oxidation reaction is equal to this much, it's a potential I will give, E naught value I will give, okay. So I will give some value, I will observe this as a some positive and write something old. So Anika, you do the same experiment and then you concentrate on the reduction process and you give us my negative value. So now, okay, so imagine we two are scientists, we did this experiment and we gave answer. What about other students? They have to study, right? Correct? So in one book they have given in terms of oxidation, in another book they have given in terms of reduction. So totally values will be confused, correct, confusing values. So therefore, yes, so this type of students or else scientists were there in the beginning. So therefore IUPAC is a standard one. So they have decided that you have to give importance for reduction process rather than oxidation, okay. Based on this they conducted some experiment and they found that whenever you take anode, so their oxidation, you have to select anode in such a way that there must be an oxidation process, and there you have to select a cathode in such a way that there must be a reduction process. Is this clear? So these two processes are fixed, you should not at it is possible to shift, it is possible to shift, but it makes confusion. So to avoid that, IUPAC gave a standard that select anode in such a way that anode means some metal you have to select, right? So their oxidation reaction must takes place and you select some cathode where reduction reaction takes place. So this is the standard. And students, you have chart, do you want to see that chart? Yes, students, you take a 5 minutes break. In my watch, it is 5:55. At that time, I will bring that chart now. Okay? Yes. Students, keep your videos on. Students, this is the value. Based on this, you can decide which one is a cathode and which one is a anode. So here almost all positive ions are there. 1 minute. Here, can you see some positive values? See here, hydrogen is the standard one. Okay, this is the hydrogen. And some positive values are there, right? So these are all are taken as anode. Okay. And then, 1 minute. Yeah, some negative values are there right here below this hydrogen. So these are all taken as cathode. So these are all fixed. So you can't expect a reverse reaction. Is this clear, Anika? So based on that, we have to decide which one is cathode and which one is anode. Yes. Students, now there are three types of refining process. That is nothing but distillation process. One more is a liquefaction process, and one more is nothing but the electrolytic refining. Is this clear? These three processes are clear? Yes. In your textbook, only three processes are discussed, and you can go for chromatographic technique, or else a refining technique, vapor phase refining, or else a zone refining. Okay. So different techniques are there that you will study it in higher class, in the sense second year. Okay, second PUC. Yes. Students, now you have studied almost all, means a total 4 steps are there in the metallurgy. All 4 steps are, we have discussed all 4 steps. Students, now you have to study according to this your syllabus. We have to study one extraction. So that is nothing but, you just write the side heading. So that is nothing but extraction of iron. Students, today you have quiz from 6:45 to 7:30. Okay. Yes. Chapter mole concept, extraction of iron. Students, now you have to apply those 4 levels, or else 4 main metallurgical process are there, right? So that is to be applied for this iron. First, go for mining. Okay, you will get a mineral, iron minerals. Students, once again, so that we have discussed in Ellingham diagram. So based on the delta G naught value, we can decide which one is more reactive, that is metal oxides, or else metal sulfides, or else metal chlorides, or else chlorides, bromides, iodides, or else in general halides. Which one is more reactive and which one is more stable? So based on that study, oxides, metal oxides are stable, and extraction of metal from this oxide is convenient as well as economical one. So students, you select some ore from this mineral. So select ore. Apply metallurgical process for this. So what you have to do? First one is crush it. Okay, prepare a powder of this. Okay, powder of this ore over. Then the second process, go for concentration technique. Students, which technique can be used for the concentration of this metal oxide or else ore? So you can use 2 techniques. Okay, you can use 2 techniques. What are those? So that is nothing but
Hydraulic washing.
hydraulic washing, as well as a magnetic separation. So if you have a hematite ore, then you can go for hydraulic washing. If you have a magnetite ore, then you can go for magnetic separation. So purify it. So maximum amount of impurities are removed. But once again, impurity is there. Small amount of impurity will be there. That will be removed at the last process. Okay, fourth process. Then go for the third process. That is nothing but isolation of metal. Okay, isolation of metal. Okay, isolation of metal. Isolation of metal, here there are 2 technique. Go for the conversion. So first you convert that metal into corresponding metal oxide. Okay, then you convert that you extract metal from that metal oxide by adding reducing agent. Okay. Okay, so this is the fourth step in the extraction of iron. So then what is the fifth step? Go for refining process. Okay, go for refining process based on the percentage of impurity. So that will study step by step. Students, is there any confusion in the extraction of iron?
What is a reducing agent?
Yes, that I will explain. Students, did you note down everything here in the extraction of iron? Students, yes, this first step is clear to me. Okay, the second step is also clear. Third step, you just either you heat it in the excess of air or else in the limited supply of air. No problem. So that is also clear. I have some confusion in the reducing agent part. 1 minute. I will stop this sharing. Navya, you want to write something here from here? Over? Yes. 1 minute. 1 minute. Give me time. 1 minute time. Students, now how to select that reducing agent? You just concentrate on the iron line here. So that reducing agent can be selected according to Ellingham diagram. Students, can you see this line? This line? Okay, this is a iron line, students. So for the reduction of iron oxide, so this is a oxide graph, okay, metal oxide graph. For this reduction purpose, I can use a two thing as a reducing agent here. So one is, I can see from this diagram, one is this graph. What is this graph? So here delta G goes on, decreases. So that is nothing but carbon line, correct? So therefore, I can use carbon as a reducing agent. So there is no confusion because its delta G value goes on, decreases. So decreases means that will be more stable. Okay. Then students, I can also use a carbon monoxide line because it intercross here. Correct? Yes. Yes, students, as I have already explained in the last class, there is a, you have to shift this point to 1073. Okay. So one unit means this much variation is there in this graph. You shift this one to 1073. Everything is to be shifted towards the right hand side. Okay. So this point is there right here. Can you see this point? Okay, this point is nothing but exactly it can be appear at around 1073 Kelvin. Is this clear, students? And now is this clear, students? Did you see this diagram carefully? Did you check? Yes. 1 minute. So now in the reducing agent, after studying this Ellingham diagram, I can say FeO is there, right? Metal oxide, iron oxide can be converted to iron by using reducing agent, by the addition of reducing agent. This reducing agents are of two types. You can use carbon monoxide as a reducing agent or else carbon can be used as a reducing agent. So when to use this carbon monoxide as a reducing agent? At a temperature, at a low temperature. Okay, at a low temperature. That means below 1073 Kelvin, I can use carbon monoxide as a reducing agent. So this carbon can be used as a reducing agent at a high temperature, at a higher temperature, okay, at very high temperature. So this is nothing but about 1073 Kelvin. I can use carbon as a reducing agent for the extraction of iron from iron oxide at, yes, at higher temperature, that is about 1073 Kelvin. Is this clear? Did you write this one? Students, 1 minute. I'll show that diagram once again.
Excuse me,
Students?
ma'am.
Yes.
You had mentioned a step of converting the concentrated ore into oxide, but the ore is already oxide, right? Fe2O3 or Fe2O4.
Yes, but heating is required. Heating is required. Even though it is there in the oxide form, students, oxides in oxides also different types of oxides are there. So that ore Fe may be there in the Fe2O3 form, or else that Fe may be there in the form of Fe3O4 form. Is this clear? So now extraction of Fe, 1 minute, I will write here. Yes, your doubt is like this. So why already it is there in the oxide form? So why I have to convert or else why I have to go for either calcination process or else roasting process, correct? Yes. See, these two are there either in the hematite form or else in the magnetite form. So that is Fe3O4 or else Fe2O3. Here from these two parts, extraction of iron is a little difficult compared to that of the extraction of iron from FeO. Is this clear? So therefore, you heat these two things under in the limited supply or else in the excess supply of oxygen. You adjust oxygen supply in such a way that you convert this Fe2O3 as well as Fe3O4 to FeO. So that all conversion process will study it in detail. Okay. So all conversion takes place at a different temperature zone. That I will explain. Okay. It's a lengthy process. Muralidhar, is this clear?
Yes, ma'am.
Okay. Students, you just concentrate on this diagram. So if you shift this point towards here, that is 800 degrees Celsius or else 1073 Kelvin temperature. So above this temperature means this one, 1073, 1088, 73, 22, 73, etc. So you can use a carbon line, correct? Because the carbon temperature goes on, sorry, carbon delta G naught value goes on decreases. Okay, you can use this as a reducing agent at a higher temperature. Is this clear? Now, can you expect that a CO line here, somewhere here? Somewhere here? No. What is this region? This region is nothing but a higher temperature region. So therefore, you can't use this carbon monoxide as a reducing agent at higher temperature. Is this clear? Therefore, carbon monoxide can be used as a reducing agent only up to particular temperature. That is, you can say, see here, intersection will be there here. Okay. So up to in and around 1073, you can use only, okay, if you extend this, at least up to 1200, you can use that. So above that, you can't use that carbon monoxide as a reducing agent. Is this clear, students? Yes. So now, is this clear? A reducing agent selection is also done. Okay. Yes. Now we'll study this process in detail. Students, extraction. This is a general framework. Okay. So the next one, actual extraction. So this is actually normal method. Okay. Then how iron is extracted in the commercial extraction of iron, commercial extraction. Okay. So now you take iron ore and then add it to a tank. Tank in the sense that furnace or else that system is called extracting chamber is there, right? So that is called the blast furnace. Okay, blast furnace. I will show you the diagram. Students, there you have to take iron ore. Okay, you have to take iron ore. Let me write hyphen here. Okay, so iron ore you have to take, and then you have to add carbon. Carbon is nothing but coke. Okay. Why? This act as a reducing agent. Is this clear? Then, in this iron ore, some amount of impurity will be there. Okay. Impurity will be there. So, to remove this impurity, you add, okay, you add limestone, that is calcium carbonate. Okay. Add limestone. So this limestone is a third reagent or a third party. So this is called as flux. Okay, flux. What is the role of limestone in this case? Okay, so here all each and individual roles are important. What is the role of FeO here? So from this you can extract Fe, correct? Fe can be extracted. Fe can be extracted. Oh, then what is the role of coke in this case? Coke role is nothing but it acts as a reducing agent. Okay, coke act as a reducing agent. And then coming to calcium carbonate act as a flux. Flux is nothing but another reagent or else chemical substance. So flux is nothing but a third reagent or else a chemical substance. So what is the role of a flux? It removes impurity. It removes gang. Gang is nothing but impurity. How? This flux reacts with the gang and you will get some product. That product is called slag. Okay, product is called slag. So that impurity will be removed in the form of a slag. Okay, impurity will be removed in the form of a slag. Is this clear? Yes, students. Now, in what ratio you have to take these three things? So, if you take, as I will write it here, students, you have ore and you have coke and you have limestone, correct? So, you have, if you take 8 amount of this, then this must be half and this must be in 1%. So the composition of ore is nothing. Ore as well as coke as well as limestone is of the order 8:4:1. Okay, that means a large amount of ore is to be taken, exactly half of the reducing agent is to be added, then a small amount of flux is to be added. Is this clear, students? Did you note down everything here? Then, students, extraction of iron is done in different temperature zone. There are so many temperature zone here. 1 minute, I will share this slide. Before that, what are the impurities which are present in this iron oxide? Students, usually you will get, see, this is the mining part. Okay, so sorry, do after mining. So along with that iron, you may contain some amount of SiO2, silicon dioxide. So this is a iron ore. It may contain silicon dioxide as a GAN. Okay, GAN. That is nothing but impurity. So to this reaction chamber, when you add limestone as a flux, then what happens? This SiO2, which was there in the ore impurity, that reacts with the calcium carbonate and it will be removed as calcium silicate. Okay, so what is this? So this is nothing but a gang, and this is nothing but flux, and this is nothing but a slag. Okay, so now impurities are removed using flux. So flux is a media which removes impurity. So the product, so that those two reacts with each other, that will be converted to slag. Students, once again, yes, that is okay. In flux also you can define acidity as well as basicity. Sorry, acidic flux as well as basic flux. Okay, acidic flux as well as basic flux. Okay. So now if this is, so for example, okay, that is not there in your book, but I will explain once. See, if this is an acid, then basic flux is to be added. Okay, if the gang is acid, then basic flux is to be added. If gang is a base, then you have to add acidic flux. Is this clear? So there are two classification under flux, acidic flux as well as basic flux. That depends upon the nature of the impurity. Is this clear?
Excuse me, ma'am.
Yes.
What is the difference between gang and slag? Like, is it easy to separate slag?
Slag, in the sense, slag can be separated from the system. Okay, it is an infusible one. Okay, it's like a molten one. Okay, that can be removed from the system. Then if you want to remove, or else if you want to separate this calcium content, means calcium carbonate content from SiO2, then you have to go for other technique, separation technique. Okay, but
So we choose slag because it is easier to separate it from the ore than gang.
no. Slag is the side product. This is unwanted material. We will not use this slag in the extraction purpose. Okay, we will use only the flux. When you add, for example, so imagine this is the reaction chamber. Okay, so here ore is there. In this, see here there is some gap, right? Here ore is there, and gang is there. Okay, ore means it contains metal plus impurity. That is nothing but gang. Add reducing agent to this reaction. Some reaction will go on, right? Then along with that, that impurity is there. That impurity, I have to remove that impurity, right? So here commercially, I can't pick, correct. So I can't pick it, or else I can't use that concentration process. Okay, hydraulic washing. Okay, that
Yes,
can
ma'am.
be done. That can be done. But this blast furnace means, see, you are heating. Okay, temperature will go up to 2000 Kelvin. So at that time I can't pick, or else I can't wash it with the water, or else a magnetic separation technique is also does not work. As froth flotation you cannot apply, and even leaching process is also useless here. So at that time what you have to do, you add a third reagent, so which combines with that impurity. You have to study this reaction. What type of impurities are there in this, and what type of the reagent is to be added. So that reagent, you concentrate on that third reagent which is added here. So that name, its name is nothing but flux. Okay. Then when that flux reacts with this impurity, we'll get some unwanted material. So that is called slag. That means slag means it contains third reagent plus the impurity, third reagent which is added to the system to remove the gang particle. Is this clear? So we will not concentrate on the slag. Slag, we have to remove this after using that. Okay, so your question is related to the slag, whether
Yes,
we will
ma'am.
use that as slag. No. Slag is, once again, it contains impurity. Okay.
So flux is just a replacement for leaching and
Ah,
hydraulic wash.
yes, that is like a concentration process. Okay, so flux is to be added to this blast furnace because temperature is very
Okay,
high,
ma'am.
right? So we can't remove impurity. So if you add this type of third reagent at that time, the maximum amount of impurities will be removed in the form of a carbon silicate. If you consider this as a impurity, then you can remove it in the form of calcium silicate. So this compound is called slag. Is this clear?
Is it easier to remove slag than gang?
So both are, is it? Yes. See, flux gang is nothing but 1 minute. See, students, imagine this is a blast furnace. Temperature, imagine temperature go up to, you can rise temperature up to 2000 Kelvin. Imagine 2000 Kelvin. Okay. So gang will be there. So I will add, see here you will heat, right? So you add powder here, iron ore powder here. So here impurity will be there, right? Gang will be there. Okay. Here temperature is less. Correct? Now you heat this. Add flux. Add flux. What happens to the temperature? Temperature goes on increases. Means what happens? Everything will melt. Correct? At that time, that flux combines with that gang particle, and then a slag will be, you can remove that slag easily. More easily than that of the, means gang pick. You can't pick that gang, or else you take these two situations. Suppose if you want to pick the gang from here, you concentrate on the temperature. Temperature is very high. Okay. Imagine you need to apply more energy, or else you have to waste your energy there. Okay. Or else if I add, so instead of that, if I add some other reagent, the automatic reaction takes place, complex is formed. So complex is nothing but not a original coordination complex. So just one big molecule will be formed. So it is there in the molten state. So now solid as well as molten, if you consider which one easy to remove, molten flows, right? So you can easily remove. Students, I will show you the diagram. So at that time we'll come to know. See, this is a blast furnace. See the temperature to 2170 Kelvin. very high temperature, and it has a side connections are there, right? The pipe. Okay. So using this, you see here, solid waste. Solid waste means this is nothing but a slag. Is this clear? Is this clear? Yes, students. Now we have to study all these process in detail. Different temperature zone. In different temperature zone, different type of reactions are possible. Okay, reduction reactions or its concentration process that is possible. Students, we will discuss only this part is left in this chapter. Okay, so and small other topics are there. So I will complete it in the next class. Okay. So students, and now it is almost a time. So you go to Ignis and then write the quiz. Okay. Yes. Then remaining thing about reaction, we'll discuss it in the next class.
Thank you, ma'am.
Okay.
Thank you, ma'am.
Welcome.